Hello everybody, welcome. Today we're going to be designing the rafter. We did the Portland. Now the video following that is the design of rafter. This is the whole truss. Just wanna let you know that this work is from here, and this is the finished product of the design. These are the complete calculation of stresses of the truss, the roof truss. Here's where the design begins. This is the roof truss we have. We designed we completed the purlin. Now we're going to design the rafter. And after the rafter is connected to the bottom cord by installing the vertical and diagonal structural member for the truss, it will become as like one truss. Alright, so we designed it step by step. We did the purlin, now we're going to do the rafter. This is the whole picture of the roof truss. There's a wall here carrying it's a concrete wall carrying the roof truss, both sides. This is the back side, this is the front side. Now, here's the load analysis for the purlin that we designed, and the purlin transfers the reactions to the rafters. These are the rafters, 4 of them, carrying the purlin, and this is the cross section of the roof of the structural member right here when you cut transverse section of the roof. This is just one unit of purlin. There are about 3 purlins for the whole roof, and at the very end of the purlin, both ends has only half of the reaction. The interior only half reaction transferred to the carried by the rafter, but and in the very end of the purlin, there's an overlapping joint there for another purlin. When you design a roof truss, especially when you want to install the purlin, when you choose your purlin, it has to be, you gotta look at the commercial sizes of the purlin. This is the commercial size, which is 3.6 meter. That exactly fits the whole length of the roof. Okay, here's the complete diagram of the roof. This is the purlin here. There are 3 of them there to complete to cover the whole roof from one end to the other. So we're solving one, and what we get there is applied to every purlins and rafter as well. Here reaction is only 1/2, since we're showing one purlin, but for the other half, in continuation of the purlin, so there are going to be 2 reactions in there, 2 halves of reactions, both at the end of the rafter and the midspan of the rafter. The midspan, the rafter is, the purlin is arranged like this, it's overlapping. Alright, like a jagged edge, and in the very end purlin right here against the wall and the edge of the rafter, we're gonna install the gutter here for the rain downspout. So it has to be spliced like this in one line. Okay, in the midspan doesn't matter, you overlap this better. So therefore At the very end of the purlin there are two reactions. So therefore all the reactions carried by the rafters right here are all the same. If you multiply this by 2 you get 3.09. So basically all the loads at every joint of the rafter, all loads carried by the rafters are the same, which is the same magnitude of load of 3.09 kilonewton. So here's the joints. Here is detail 1 applied here and here, and the detail number 2 is applied in the midspan. That's how you splice the purlin. Okay, you have the reaction there. I explained to you these all their loads are gonna be the same. It's 3.09 kilonewton each joint of the rafter. And there we go. There's the applied load now. This is not gonna fit in one video because there's a time limit for the YouTube as well. So I don't know if you can fit this, but I think there's 2 videos of this process, the design of the rafter. Here we go. Here's the load. Here's the 3.09 kilonewton uniformly distributed load, uniformly equidistance and same magnitude. So therefore they are considered as uniformly distributed load. The rafter is inclining 16 degrees right here. The weight, the 3.09 is a gravity load, is the roof load including the weight of the purlin as well. And the direction of that load is a vertical load. The direction of that load is it's a gravity load. It's directing towards the ground as your reference, so 90 degrees to the ground. The direction of that load. So, and since this is an inclined surface here, the rafter or the top chord, this applied load is considered to be an inclined load. Any inclined load should be resolved into 2 components of load, one horizontal, the pH, and one vertical. So we're going to resolve, first we're going to calculate the magnitude of all these loads. So 3.09 times 8, there are 8 of them, and the magnitude of that load is 24.72 kilonewton. It's one of these, we're going to solve one by one each magnitude of one gravity load by resolving it into horizontal and vertical component. And the solution for that is right here. See, that's the 3.09 is the gravity load directing toward 90 degrees to the ground. Now we're looking for the Pn. The Pn is the normal, is the load normal perpendicular to the rafter, and the pH, the horizontal component of the gravity load, is parallel. The direction is parallel to the rafter. The horizontal load will tend the roof to slide off the rafter, and assuming that the purlin and the whole roof is fully secured to the rafter. Therefore we have to consider the pH as well. This is not a wind load. The wind load is included here already. So this is the gravity load. This is the gravity load in a horizontal direction, inclined direction, bringing all this roof down, sliding off the rafter. So therefore we have to consider the pH as well in our calculation for the reaction. So resolving 3.09 into 2 components of pH and Pn. The pH here, when you look at this, is the 16 degrees right here. The pH is the opposite side. Therefore, when you see opposite side, that involves the sine function of the trigonometric function, and the Pn, this is the Pn. The function for that in the trigonometric function is a cosine. It is adjacent. So you can choose any of these trigonometric function here and solve for the components, two components of loads. So to solve for pH, here's the horizontal vertical components. First we gotta solve the Pn. The Pn is 90 degree here. 90 degree load with respect to the rafter. So the Pn is cosine, so cosine 16 degrees is the adjacent, that's the adjacent there, divided by the hypotenuse. Hypotenuse is known, the only unknown is the adjacent side, so therefore we can solve the Pn by using cosine function of a trigonometric function right here. So cosine 16 degrees was Pn divided by 3.09. P now is called the cross multiply this equation, you get the Pn, it's called cosine sine times 3.09, you get 2.9703 kilonewton per one normal load. Okay, that's individual. Alright, here it is applied here, I draw it here. 2.903 kilonewton, and now for the pH. Right here, this is the pH, the horizontal component. Horizontal component pH, that's the opposite side, so therefore we can use the sine function using the hypotenuse right here. This is the known. We know this is the gravity load, right? So sine 60 degrees is the opposite over hypotenuse, and the cross multiplying this we get cross multiplying pH, it becomes sine 16 degrees times 3.09, you get 0.852, and that's my license plate. Alright, so we have the individual horizontal vertical components now. To apply that to the rafter, you have to calculate the magnitude of that load, the total of that load. So you multiply it by 8. Multiplying that 8 by 8, the magnitude of the Pn is 23. The final total load of Pn, the load normal as we resolve it, is 23.76, and the total horizontal component 0.852 multiplied by 8, you get 6.816 kilonewtons. So we have that loads now applied. This horizontal and vertical component, if you use the magnitude of this load, it should be applied at the midspan, at the midpoint of the rafter. Okay, so we have the bottom chord here as 5 meters. We can solve the length. How long is this? The length of the rafter by using the truss triangle. Here is the truss triangle representing the truss right here. The rafter represented by X right here, and the total height of the truss is represented by Y. We solve both that, this length and the height. To get that height, to get that X is the rafter, and since we have the adjacent side here, this is the angle, 16 degrees. Since it includes the adjacent and the hypotenuse, you look at that function here. So adjacent and hypotenuse, so we go cosine. So therefore we can use cosine function. So therefore to solve for x, right here, solve for x, use cosine 16 degrees adjacent over hypotenuse, substitute the value and cross multiplying it, it becomes 5 over x x is equal to 5 divided by the cosine. By cross multiplying this, the sign goes down here and the x goes out there to be the unknown, and we can solve it. Solve this, calculate this, you get 5.2 meter. And you gotta look at that too. The bottom chord is 5, therefore this is longer, so it's 5.2 is correct. So this is 5.2. I put it right here. Here it is, 5.2, the length of this problem. And this load here, the horizontal and vertical component is applied to the midspan of that. So the midspan of that is 2.6. Okay, now to get the height, again you gotta use the trigonometric function. The height is opposite side, the y is opposite side, therefore we can use sine 16, opposite over hypotenuse y over 5.2. We use the hypotenuse there, cross multiplying it, this 5.2 goes here, so y is equal to sine 16 times 5.2. It gives you 1.433, the height of that. So we have that information now that we need to take the moment to solve for a reaction. Okay, let's do one check first. We solve this pH and the PN and the pH, the horizontal and vertical components of loads. We're gonna make sure that we can check this by using the we can check if these values here are correct. To check that is by using the trigonometric, using the theorem of Pythagoras, the Pythagorean theorem. Here, Pythagorean theorem states that the length of the longest side of the triangle is equal to the square root of the sum of the squares of the two shorter sides. So we formulate that definition there of Pythagoras, the theorem, the Pythagorean theorem. C here is the C is the hypotenuse. This is the 3.09. We need to get that to make sure our pH and the PN, these two are correct. So you gotta check that. So 3.09 is the C, is equal to the square root of 0.852 square plus 2.9703, square that and take the square root of it, and we get the same. 3.09 is equal to 3.09. Therefore the pH and the PN are correct. So we should check that, because or else we don't want to continue with the wrong information and wrong values there. Alright, so now we have all completed: the height, the length, the distances, and the loads. The magnitude of the PN is 23.76 and the magnitude for pH is 6.816. Okay, now here's how we attack this problem. Okay, now we have all these. We have all the loads there, 23, and the horizontal component 6.816 applied midspan of this is the rafter right here. and the lever arm, the distance of that midspan there from point C to the midspan is 2.6, and so as the from B to the midspan is 2.6. It's in the middle, okay, of that span there. Now to solve for the reaction RA and RB right here. The reactions here, RA and RB, the direction of the reactions are parallel to the applied load, the PN, the normal load. So you get the inclined reaction RA and RB there with the same angle. Okay, so solve for the reactions. You need, this is an inclined load, we need the lever arm. The lever arm for the applied PN right here, the distance from here up to the C is 2.6, but you have to draw a line parallel to the line of action to get the horizontal, the perpendicular distance of the line of action to be the lever arm. The lever arm for there are calculations of the lever arms. The lever arm for PN, when you take a moment at A, or either way, we need to determine the lever arm first. Both horizontal, this, horizontal and vertical. We need a lever arm to take the moment and get the reaction RE and RB. So solve for lever arm. Lever arm. Okay, now you take a moment at A. The lever arm for PN is x1 is equal to 2.05. How to get that? The lever arm for the PN is only up to here. You draw a parallel line to the line of action, and that 90 degrees to the rafter. And we have to solve for the x and subtract it from 2.6 to get the actual lever arm of the PN. Alright? So to solve for the x there, to solve for x, we need a trigonometric function. And x at the opposite side, this is the 90 degrees side, this is your angle, 16 degrees. So since that's opposite side and we know the height here, the hypotenuse, this is the hypotenuse now, this is the adjacent side, this is the 90 degree, x is opposite, this is the angle, 16 degrees. So x is these, we can use sine function. Sine function, solve for x. Sine x now is equal to sine 16 degrees times the hypotenuse is 1.433. This is the hypotenuse here. It gives you 0.395. Alright, the x, that little x there is 0.395. So to solve for the lever arm for the PN, the x1 is equal to 2.6 minus x. 2.6, x1 now is 2.6 minus 0.395 is equal to 2.205. So that's the lever arm there. Okay, and now again another lever arm for the horizontal component right here. Alright, you solve for lever arm, that's the y, the 90 degree perpendicular to the line of action. And the definition of moment, when you take a moment at A, you have to use the definition of, follow the definition of moment. What is a moment? A moment is a product. Moment is the product of the applied load, okay, multiplied by the lever arm that is perpendicular from the line of action. Perpendicular, okay, perpendicular from the line of action to the axis of rotation. If you choose this as your axis of rotation, perpendicular distance there is the 90 degree. These two lines cross together, the line of action and the line 90 degrees to the axis of rotation. So that is the definition of moment. So the lever arm for PN is not this one here, no. You gotta look for 90 degrees intersection line there. So perpendicular distance from the line of action to the axis of rotation, and same thing with the horizontal load. We gotta look for the 90-degree perpendicular distance, and that follows the definition of moment. The pH right here, the lever arm is not this one here. No, it's not 90 degrees. The 90 degrees right here. So we solve for y. Y is, well, that's a cosine function. This is the angle here. When you see adjacent side right away, it is using hypotenuse there right away, it is a cosine function. So y is a cosine 16 degrees times that hypotenuse there, 1.433. The y, the lever arm, is 1.377. So I plug it right here. So that's the y, perpendicular distance. So now we have that already. Now we gotta start solving for reactions RA and RB. We gotta solve for RB first. Summation of moment RA is equal to 0. Here you can assign your own sign convention. Once you assign it, you use it all the way from the beginning up to the end. You never change it, or else you get wrong. Here I assign the clockwise rotation as positive and the counterclockwise negative. And now here's the two loads we're gonna consider when you take a moment between at A or B, the horizontal and vertical component. This is the gravity load, and then we resolve it. See, it's nicely done right there. Resolve it into two components. Now if you take a moment at A, I'm going to show you how this thing, the pH, these two loads here, a moment at A, the pH and the plane will rotate as clockwise rotation. Okay, the rotation follows the arrow, the direction of the arrow. The direction of the arrow is downward, and this is to the right. So this is how this two rotates by moment. When you take a moment, at A, these two loads here will rotate like this at A. See, according to the arrow, we rotate. What is that rotation there? Okay, that is a clockwise rotation. It will rotate according to the direction of the arrow. So if you take moment at A, these two forces will rotate clockwise rotation. So that's positive. So here we go. Summation moment RA is equal to 0. The RB is rotating. It will rotate counterclockwise. So minus 4 point. And the RB, the lever arm for RV is the 2.6 plus this 2.205, so it becomes 8.05. So 4.805 RB is negative, and the 23 again is positive clockwise rotation, multiplied by multiplied by the lever arm. This is 2.205. We solve that. The 90 degree perpendicular to the line of action, and then the horizontal component 6.816 right here, and then multiply by that by the lever arm of y, which is 1.3577 is equal to 0. That is the first condition of equilibrium by moment. Now, to solve for RB, this is in one whole equation.